This video is an investigation into the physics of a conical pendulum. You're probably already familiar with a simple pendulum, where you take one end of a string and you attach it to a fixed point, and the other end of the string has what we call a bob, or a mass. And if you take that mass and you pull it back away from the equilibrium position and let go, it swings back and forth, left and right, in a circular arc. Here we have a conical pendulum, which is set up in kind of the same way, but instead of allowing it to swing back and forth in a circular arc, we instead give it a tangential speed, which allows it to move in a horizontal circle. So maybe you can imagine in the picture that I've drawn that yellow mass at the end of the string to be moving in a horizontal circle that would be given by that circular dotted line. So in this video, what I'd like to do is I'd like to start thinking about the circular motion and the forces acting on this conical pendulum in order to understand how a conical pendulum works a little bit better. Typically, when investigating a conical pendulum, there are a couple of variables that we need to label in this diagram in order to talk about some of the features of the pendulum. One of those variables is the radius of the circle that the bob is moving through. And so the radius of that circle here we'll call r, lowercase letter r. And another variable that will be important is the length of the string. So here the length of the string would be the point from where it's attached to the ceiling all the way down to the mass that's attached on the other end. The next thing that I'd like to do is label the angle that the pendulum makes relative to the vertical. So the angle between where the string actually is and where the string would hang if it were to be at rest completely vertical. So this angle here. The next thing I'd like to do is consider the forces that would be acting on the mass. And first I know that the mass has a weight, a gravitational force that points straight down. And so I'll draw a downward force vector, and that force vector has a magnitude mg if the ball has a mass of lowercase letter m. The ball experiences one other force, and that is the tension force from the string. And so that tension force points along the direction of the string, and here I will label that tension force F subscript T. Next, I would like to consider the motion of the ball. Now, I know that the ball is moving in a circle, and let's suppose that the ball is moving at a constant speed v. A lot of the times, if you see something like this in a physics classroom, the conical pendulum would be made by a pig or a cow that flaps its wings, or a plane that is able to propel itself. And so here I just have a ball that's drawn there, but imagine the object moving with a constant speed v as it moves through that circle. If that were the case, then we would say that it's in uniform circular motion because it's moving with a constant speed v and is in a circle with a constant radius r. And so for that reason, it should experience a centripetal force that points towards the center of the circle. And so in this case, we have to ask ourselves, which force is providing the centripetal force, the centripetal acceleration that this object would experience, the acceleration that's necessary in order for its velocity to change direction and keep it in a circle. And in this case, it only experiences two forces. mg points straight down, so that's not responsible for the inwards center-seeking centripetal force. But a component of the tension force does point towards the center of the circle. And so what I'd like to point out now is that the tension force that I've drawn could be drawn as two components. A vertical component, which looks like this, and a horizontal component, which looks like this. And so I'm going to call the vertical component Fty and the horizontal component Ftx, the x and y components of the tension force. What I notice immediately about this triangle is that this angle here is also theta. The two thetas that I have drawn in the diagram, the theta made by the string in the vertical and the theta in the tension force vector triangle, those two thetas are alternate interior angles. And for that reason, they are the same. And what I realize now is that all of the forces in the free body diagram are now resolved into x and y directions. And what I could do is I could think of up as the positive y direction and towards the center of the circle as the positive x direction, and use that coordinate system to help me write Newton's second law of motion equations for this mass at the end of the conical pendulum. So I'm going to be writing a Newton's second law equation for the x direction and a Newton's second law equation for the y direction. And in each case there, the net force in that direction will be equal to the mass times the acceleration in that direction. Now, of course, we know in the vertical direction, the acceleration would be 0 because it's not accelerating up and down. In fact, it's not even moving up or down. It's moving in a horizontal circle. And for that reason, the net force equation for the y direction is quite simple. There are only two forces, and the right-hand side of the equation will be 0. Because upwards is positive, I should write positive Fty minus mg equals 0. And the next thing I'd like to do is to get rid of this Fty and replace that variable in terms of a couple of the other variables that we have. So I happen to know that I can express Fty in terms of the total tension Ft in theta. For this conical pendulum, I happen to know that the cosine of theta is equal to, for that force vector triangle, the adjacent side over the hypotenuse. The adjacent side is Fty, and the hypotenuse is Ft. So I can write Fty is equal to Ft cosine theta. And so I will now rewrite my Newton's second law equation to say Ft cosine theta minus mg equals 0. And because the net force in that direction was equal to 0, of course these two forces are equal to one another. And so here's one of the two equations that we need in order to better understand what's going on with this conical pendulum. Now for the x direction. I'm going to write a similar equation here, but in this case, the acceleration is not 0. And I know the acceleration is not 0 because in the x direction, the mass happens to be moving in a horizontal circle, which requires a centripetal or center-seeking acceleration. So the one force that happens to point in the x direction is Ftx, and that one force will be equal to the mass at the end of that string times its centripetal acceleration, which we can label AC. Just like we did for the vertical direction, I'd like to now replace Ftx in terms of variables like Ft and theta. And so the sine of theta for that force vector triangle happens to be equal to Ftx, the opposite side, over Ft, the hypotenuse. And so Ftx is given by Ft sine theta. And so once again, we can use the expression that we just found and substitute it in for Ftx this time. So here, Ft sine theta is equal to mass times the centripetal acceleration, which we know always has the form v squared over r. So v is that constant speed that the mass has as it's going around in a circle, and r is the radius of that circle. And so Ft sine theta equals mv squared over r. And so here are my two Newton's second law equations, one for the x direction and one for the y direction. And it's important to know that while every conical pendulum can be with a different speed or a different angle or a different radius, a different mass, the key thing here is that for any sort of conical pendulum where a thing's moving in a horizontal circle, these equations will always be true. And so now how can we use these equations to better understand some features of the conical pendulum? One common question that's asked about a conical pendulum is, if I take it out and I throw that mass and it's moving in a circle, can I figure out how fast it's going? Can you give me an expression for the speed of the mass that is the conical pendulum? And so the answer lies somewhere in, can we combine these equations and simplify them, removing some of the variables that would be difficult to measure? And so the first thing we might do is remove the tension force, because that might be a difficult quantity to measure in an experiment. And so what I'll do is I will first take one of these equations, solve it for the tension force, and plug it into the other. And so what I'll do is I'll take the equation on the right, which could be written as Ft equals mg divided by cosine theta. If I plug that expression in here, in the equation on the left, I will get mg divided by cosine theta times sine theta is mv squared over r. And of course, then we can see on the left that we have sine theta divided by cosine theta, which would be equal to tan theta. And so on the left-hand side, we have mg tan theta, and the right side mv squared over r. So remember, the v on the right-hand side of this equation represents the linear or tangential speed of the mass of this conical pendulum as it swings around in a horizontal circle. If I notice that there's an m on the both sides of this equation, I can cancel those m's and then multiply both sides of the equation by r and square root both sides of the equation, and I would get v equals the square root of rg tan theta. This equation represents the speed that mass will have as it moves in a circle. And notice how the speed depends on how large the circle is, and the angle and the strength of the gravitational field that the ball is in. If you wanted the pendulum to move in a bigger circle with a larger radius and a larger angle, then you would need to give it a greater speed. And that makes physical sense. Or you might imagine that if you took that ball and you tossed it or gave it a tangential speed as it was spinning around, it would eventually spiral in. The radius would decrease, and as it slows down, the radius is decreasing, and that's the relationship that I see here in the equation for the speed. And so the equation seems to make physical sense, which is always good. I would like to go a little bit further and take the equation that we have for the speed and start to think about a few other variables that can characterize a conical pendulum. One of these variables is the amount of time that it takes for the ball to complete one full cycle of its motion, to go around the circle once. And the quantity that I'm talking about is the period of the pendulum. The period of the pendulum, which we typically write as a capital letter T, is related to the speed and the size of the circle. If we know that in general speeds are given by distances over time, if they're moving at a constant speed, then the distance that this mass would travel as it goes around in a circle would be equal to the circumference of the circle, 2 pi r. And the amount of time it takes to complete one full cycle of this circle is the variable that I was just describing, the period, capital letter T. And so if I look back at the equation that I have circled there, I remember that v squared equals rg tan theta. And if I know that the speed of the ball is also given by 2 pi r over the period, then I could write the speed squared, which would be 4 pi squared r squared over t squared, is equal to rg tan theta. And the reason why I think this equation is interesting is because if we solve the equation for lowercase letter g, the acceleration due to gravity, we get 4 pi squared r, meaning we would have to divide both sides by r and one of the r's would cancel, divided by t squared tan theta. And this is interesting because I could use a conical pendulum to measure the acceleration due to gravity on a planet. And the only thing that I would need to measure the acceleration due to gravity would be the radius of the circle, the period, or the amount of time it takes for it to go around once, and the angle that the pendulum makes with the vertical. I hope you can appreciate that in order to measure a variable like g or the period or the speed, you're never going to be able to remove the angle from the equation, right? The angle is a defining characteristic of the conical pendulum, and that's why every equation that we write has an angle in it that just simply can't be reduced or removed from the equation. And in this equation for lowercase letter g, we have a tan theta in that equation. Let's suppose now I actually gave you the task of measuring the acceleration due to gravity using a conical pendulum. You might write out these equations and arrive to this point, and when you got here, you'd realize that you would need to measure the radius of the circle, the angle that the string makes with the vertical, and the period. And I would argue of those three variables, the easiest one to measure would be the period. Right? If you had a stopwatch, you could start your timer at one location, let it go around once, and when it returned back to that same point, you could stop your timer. Or to reduce uncertainty, you could let it go around several times, find the time for 3 or 4 or 5 periods, and then divide by 3 or 4 or 5 to find the time for one period. And there's no way of removing the angle from the equation, and so somebody's going to have to get up there with a protractor and measure that angle. But r, I think, is a variable that not only would be quite difficult to measure precisely in an experiment without the use of a video or some fancy piece of equipment, not only would it be difficult to measure, but it can also be removed from the equation and can be written in terms of things that we either already have to measure or are easier to measure. The way that I'm going to show this is I'm going to first draw a triangle. And this triangle has one leg that is equal to the radius of the circle. So in the picture that I have drawn up above, the mass at the end of the conical pendulum would be here. And that means that the length of the string would be this side of the triangle. This angle in the triangle would be 90 degrees. And this angle that I've drawn is theta. And the reason why that is important is because I could express r in terms of L and theta. In this triangle, I happen to know that the sine of theta is equal to the opposite side, which is r, over the hypotenuse, which is L. And this means that r is equal to L sine theta. And as somebody who might be interested in physics or experiments, this is an important thing that I've just done here. I have taken a variable in an equation, lowercase letter r, and I have found a way to express that variable in terms of other things that I already have to measure or are easier to measure. And what I mean by that is, if I write r instead as L sine theta, then instead of having to measure the radius of that circle, I can now measure L, which is simply the length of the string, and I can do that without the thing even moving. I can bring the thing back to its equilibrium position and carefully measure the length of the string. And theta already had to be measured because it was in the denominator of the equation. So I think if I was doing an experiment where I was measuring the acceleration due to gravity using a conical pendulum, I would use the equation g equals 4 pi squared, and instead of r, I would write L sine theta divided by t squared tan theta. And of course, those of you who are following along, you know that sine theta over tan theta happens to be equal to cosine theta. And so this equation could be written more simply as 4 pi squared L cosine theta over the period squared. And I think that that might be the most simple expression in terms of doing an experiment where you use a conical pendulum to measure the acceleration due to gravity. The very last thing that I'd like to do is take a look at this equation, but instead look at the equation solved for the period. If I take that equation that I have boxed at the bottom right-hand corner of the screen and I solve it for the period, I'll leave the math up to you. I would get 2 pi times the square root of L over g times the cosine of theta. And the reason why I think that equation is interesting is because if you look up or remember the period equation for a simple pendulum, that equation is simply 2 pi times the square root of L over g. And so maybe you can start to think about the physics of how a simple pendulum is different from a conical pendulum, and how the equation for the period, the time it takes for it to either swing back and forth once or around in a circle once, those equations are so similar, except for the conical pendulum, you have to include the cosine of theta underneath the square root.